What is the Doppler effect? According to Petranica, the Doppler effect is defined as an apparent difference between the frequency at which sound or light waves leave a source and that at which they reach an observer, caused by relative motion of the observer and the wave source.
We would like students to understand what the Doppler effect is, its real-life examples, relevance and applications, history, and physical explanation behind its creation.
The Doppler effect was named after Austrian physicist Christian Doppler in 1842. Frequency and wavelength share an inverse relationship in the Doppler effect. It can be explained as either blue shift or red shift. Blue shift occurs as the frequency increases or the waves emitted compress closer to the observer. However, red shift occurs when the waves are stretched further away from the object. Astronomy began to study the Doppler effect when it became a visible part of the electromagnetic spectrum. Now astronomers use it to calculate how fast objects or stars move towards or away from the Earth. The equation is given where c is the velocity of waves in the medium, Vr is the velocity of the receiver relative to the medium, Vs is the velocity of the source relative to the medium, f is the observed frequency, and f0 is the emitted frequency.
When a moving source of sound is approaching a relatively stationary observer, each following crest of the sound wave is emitted slightly closer to the person than the previous cycle of a wave. Because it is closer, it takes less time to reach the observer than the previous cycle does. As a result, there is an increase in frequency because the time it takes for the next cycle of waves to be observed is reduced. When the waves travel together, they are pushed together and overlap each other, causing the distance between each individual cycle of waves to be shortened. Following the same logic, when the source of sound moves farther or moves away from the observer, each following crest of the sound wave is emitted slightly farther away from the person than the previous cycle. Therefore, the time between each wave cycle is increased, which in turn lowers the frequency and causes the waves to spread out more. The overall effect depends on the medium in which the wave travels in, water, air, etc. The motion of the source, the motion of the observer, and the motion of the medium all play a role.
To better understand the Doppler effect, we will examine a real-life example that most people have experienced. Say you are walking at a crosswalk and hear a siren blazing truck or honking car pass by. As the vehicle is moving closer to you, the sound waves in front are compressed and occur at a higher frequency, blue shift, which you perceive as a higher pitch. As the vehicle passes, the sound waves are spread out and are at a lower frequency, red shift, and you perceive a lower pitch. The driver, however, hears the same sound because the driver is at a constant position relative to the sound source. Another real-life situation that several people know of would include police cars. If you've ever seen a police car stationed on the side of the road quietly, they are mainly checking the speed of passing vehicles through the use of their radars. The Doppler effect comes into play during this example, as the sound wave frequencies of the passing cars continue to increase until it passes the police officer's car. Following this, the frequency rapidly decreases. The sudden change from high to low frequency is due to this effect. This change is twice the ratio concerning both the velocity as well as the speed with which the police radar was affected by the passing vehicle.
Another real-life example all of us have experienced would include weather storms. In order to track current and future storm locations, meteorologists use their Doppler effect radar. Oftentimes, they find out the direction as well as velocity of precipitation by detecting the type and direction in which the winds are moving at that specific time. Through this, we are able to have an estimate of when and what kinds of storms will occur in regions around us. The Doppler effect is also used for medical purposes, such as in echocardiograms, to detect blood flow and velocity. This helps doctors detect blood flow leakage as well as issues such as miscommunication between the left and right sides of the heart and vascular problems, such as stenosis. Another application is seen during satellite communication when satellites are traveling fast. The Earth's curvature changes while spinning. In order to accommodate for this, the Doppler effect can be used to change the frequency of the signal and allow for a more constant frequency transmission.